go on from. Okay, so the concept that you guys got introduced to yesterday is similar to work energy theorem. Okay, it deals with the fact that energy can't be created, it can't be destroyed, but it can be, let's say, traded, given, or lost. Okay, in the work energy theorem, when work is done, that work is gained or lost as mechanical energy to or from an object. But the amount of energy is always conserved. Okay, you guys did a bow and arrow example in this one earlier where they talked about if I had a bow and I drew it back using 100 newtons of force, a half a meter, okay, have I done work? Yeah, right? I exerted a force through a distance. So I could easily say that, yeah, work equals force times distance. Okay, and if I was using the numbers from the example yesterday, that would be 100 newtons times 0.5 meters. That means I did 50 joules worth of work. That is now all the energy that is going to be in the bow arrow system. Okay, so if I did 50 joules worth of work, how much elastic potential energy is now stored in the bow? I did 50 joules worth of work drawing back the bow. How much elastic potential energy is now stored in the bow? 50 joules. That's the law of conservation of energy. Energy can't be created and it can't be destroyed. If I do work on something, that energy has to go somewhere. It goes from me as work to the arrow or to the bow arrow system as mechanical energy. In this case, potential energy in elastic form. Now, if I let the string go and the arrow flies out, what is the bow doing to the arrow? Pushing it. How much work can it do on the arrow? 50 joules. How much kinetic energy will the arrow have when it leaves the bow? 50 joules. That's how the law of conservation of energy works. It says energy can't be created and it can't be destroyed. It's always going to be accounted for somewhere. Now, the bow and arrow system is kind of a classic. Okay? It's fairly simple. We're not accounting for energy that's lost to sound and heat and other things like that. And even if those are lost, they're still accounted for. Okay? They're not destroyed, they're just in another form. Okay? The stuff we do is going to be all pretty simplistic, slingshot, bow and arrow, things like that. Okay? Does that make a little more sense from yesterday? Okay. So when it comes right down to it, the law of conservation of energy says this. Since energy can't be created and it can't be destroyed, the mechanical energy of a system, like the bow and arrow, is always going to have the same amount of energy at any two conditions. That would be initial and final. So the initial mechanical energy of the bow arrow system was 50 joules. It was all in the form of elastic potential energy. When I released the bow, it did work and transferred all of its mechanical energy to the arrow. And then at the end, the arrow still had 50 joules of kinetic energy. Everybody okay with that idea? Okay. So what we'd be saying in that situation is this. Okay? The initial energy of the bow was 50 joules. The final energy of the arrow was 50 joules. The energy was conserved. Where we're headed is a calculation kind of like what we've done before. Okay? It's kind of like a work energy theorem question, except we're going to kind of take the work part of it out and just compare the energy of a system before and after some conversion occurs. Okay? Our situations are always going to be converting potential energy, gravitational potential energy, into kinetic. A roller coaster is a classic example. Okay? A sled sliding down a hill, a rock being dropped off a cliff. Okay? Those kind of things are all classic conservation of energy questions. All right? Everybody with me there? So the challenge with a conservation of energy question is the same as it is with a work energy theorem question. I have to identify what kind or kinds of energy an object has at point 1 and then again at point 2. Okay, so let's look at kind of a simple example here. All right, let's say I've got a ball on a hill. Okay, and my initial point is going to be the ball sitting on the top of this hill that is 20 meters tall. If you're not writing this down, you should write this down. Okay, and you can write conservation of energy introductory example. I'll write that on the board. Okay, so a conservation of energy question is going to want you to calculate either a height or a speed at one of the two positions based on the information that you're going to get. Okay, so in this question, the information we're going to get is going to go like this. There is a ball, a 3 kilogram ball, sitting at the top of a hill. Sitting, not moving, sitting at the top of the hill. The hill is 20 meters tall. How fast is the ball going at the bottom of the hill? Okay, that's a kind of basic, typical question. So, what are our givens?
Mass.
Mass. I've got mass is 3 kilograms. Okay, so mass equals 3.0 kilograms. All right, what else am I given? Right, initial? Initial height. Am I also given the final height? What is the final height? Right. I'm given one other thing. Okay, I am given that. Wasn't what I was thinking of, but you're absolutely right. Ball is sitting at the top of the hill. Initial velocity, what is it? 0. Okay, from that information, and this is something you already know how to do, I need to determine what kind or kinds of energy the object has at its initial point. This will be its initial point, okay? This will be its final point. Agreed? Okay. So, since this question doesn't mention energy being lost or work being done or anything like that, then there's no change in energy, because that's what work is, right? There's no change in energy here. Nobody's pushing the rock, okay? So if there's no work being done, that means the energy at the top of the hill and the energy at the bottom of the hill are equal. In other words, the mechanical energy of the ball will be conserved. It will have the same amount of mechanical energy at the bottom of the hill as it has at the top. Okay? Will it be in the same form? Okay? What kind of energy does it have at the top of the hill? Potential, right? It's not moving, right? Now, yesterday you learned that mechanical energy is the sum of an object's potential and kinetic energy. You did a question with a seagull carrying a clam and a high jumper and stuff like that. Okay? So if I want to calculate mechanical energy, I add EP plus EK. That's what this formula means. This formula means initial mechanical energy equals the final mechanical energy. Okay? So we would write this out. We would expand it out to say this. The potential energy initial plus the kinetic energy initial equals, same thing on the other side, but final. EP final plus EK final. Okay, that is how we calculate mechanical energy. We're saying the same thing. Both of those lines are mathematically the same. They're saying my initial mechanical energy equals my final mechanical energy. Now, at this point, I kind of skipped ahead. We already identified that at the top of the hill, it only had, what kind? Potential energy. Okay, so that's going to be 0. Adding 0 doesn't do anything, so I can get rid of that. Can I get rid of anything on the final? What does it not have at the bottom? It doesn't have any potential. Potential would be 0. Okay, so that's very similar to what you did in work energy theory. You had to identify what kind of energy was being changed. In this, you have to identify what kind of energy is present based on, is it above the ground? Is it moving? If it's above the ground, it's got potential. If it's moving, it's got kinetic. We'll do situations where it's got both kinds on both sides. Okay? It doesn't make them really any harder. Okay, so now I'm saying the potential energy initial, so the energy here at the top of the hill, is equal to the kinetic energy at the bottom of the hill, which we already established was true. Do I have formulas that calculate potential and kinetic energy? Okay, those you also learned yesterday. Okay, the potential energy of an object, okay, and we've been using this formula for a while already, okay, is mass times gravity times height. Okay, and for kinetic energy, okay, question initially wanted to know how fast is the ball going at the bottom of the hill. Can I now solve for that? I can. Okay, this is really not a lot different than doing a work energy theorem question in terms of the algebra. I just need to move half an m over to this side. Hey, I got an m on the top and m on the bottom. I can cancel them. In fact, when we get into more complex ones, you're going to find that mass cancels a lot. I'll still give it to you. It doesn't hurt to put it in, but you don't have to. I'll show you that later. Okay? But for right now, of course, mathematically, there's no plus and minus here, so I can cancel those two m's. They're the same number anyway. Okay, so what I have is GH initial over mass equals VF squared. But I only want VF, so what do I have to do? Square root. Just like we would have, work energy theorem question, right? This is like the work on the top divided by mass.
Isn't it divided by?
Sorry, divided by half, not mass. Good catch, Olivia. I haven't had enough coffee yet. Okay, so I've got the square root of GHI, okay, divided by 1/2. That's now going to calculate VF. All right, so VF will equal 9.81 times 20 meters. That was our initial height. Divided by 1/2. Okay, so 9.81 times 20 divided by 1/2, square rooted. Okay, so at the bottom of the hill, it'll be going 19.8 meters per second. Okay, mathematically, it's not any more difficult than what you've been doing already. Okay, fundamentally, we can use some of the stuff we learned in work energy theorem, like identifying what kinds of energy are present. That's something we have to do for this, but we put them in a different context. Okay, in a conservation of energy question, there's no work being done. Okay, in a work energy theorem question, obviously there is. Okay, so how do you tell the difference? Like if I give you a question on an exam, how will you know it's a work energy theorem question or a conservation of energy question? Because it kind of seems like they give you similar stuff, right? They give you heights and speeds. Okay? Did it give you force? Force will never be part of a conservation of energy question. If a force is present, it's doing work, then it's a work energy theorem question. Okay? So if a question gives you or asks for force, it's a work energy theorem question. You'll never get that in a conservation of energy question. Okay? You'll also get distance, obviously, in a work energy theorem question. You'll get heights here. And the other thing is, at least in Science 10, in a conservation of energy question, you'll get speeds and heights. Will you ever get that in a Science 10 work energy theorem question? No, because in a Science 10 work energy theorem question, either kinetic energy is changing, and you'll get 2 speeds, or potential energy is changing, and you'll get 2 heights. In a conservation of energy question, you could get 2 speeds and 2 heights. Okay, so you can kind of tell them apart by their givens, but also by the context of the question. If it sounds like something's doing work, it's a work energy theorem. If they're talking about pushing something, or pulling something, or lifting it, or accelerating it, those are all things that involve work. Letting something do what it would naturally do is a conservation of energy question. If I put a ball at the top of the hill, it's naturally going to roll down. That requires no work from me. Okay, if it's there, it's going to roll. Simple as that. No work has to be done for that to happen. Okay, if I drop something off a cliff, okay, it's just going to fall. I don't have to do anything about that. Okay, it's just going to fall. Everybody follow? Okay. Okay, so prime example here. Conservation of energy. Actually, just finished doing this with my physics 20s. So this is my ghetto physics pendulum. Okay, so what happens when you cut money from education? You get physics demonstrations made out of a roll of athletic tape and the drawstring from my hoodie. Okay? So in this situation here, okay, the pendulum's not swinging. Okay? Does it have any kinetic energy here? Okay. If I pull it out to here, have I done work? Okay, is there now energy in the system? Okay, if I let it go, what's going to happen? Okay, as it's swinging, what is it doing to the potential energy that I gave it? Say it. Turning it into kinetic. Right? As it swings through its arc, it speeds up, slows down, speeds up, slows down, speeds up, slows down, speeds up, slows down. Right? It's just constantly converting the initial amount of mechanical energy that I gave it, okay, in the form of potential energy, into kinetic. If this was a perfectly isolated system where there was no friction or anything like that, this pendulum would swing forever. And I'd hypnotize you all and you'd be clucking like chickens. Okay? But it would just go back and forth, back and forth. Right? That's conservation of mechanical energy. There's no work being done here. Okay? I mean, yes, I did work to lift it to here, but that's not what the question would be asking about. It would say the pendulum has an initial height of this many meters. Okay, how fast would it be going at its lowest point? Well, at its lowest point, we'd assume the height would be 0, and all of its energy would be when it's swinging through here. That's where it's going the fastest and has no potential, so it would only have kinetic. Okay, so this is its maximum point out here. This is where it's going the fastest. When it's here, halfway in the middle, does it have both kinds? Some potential, some kinetic. That's the kind of things we're going to be dealing with when it comes to law of conservation of energy. Here's the thing we have to remember about law of conservation of energy. The total mechanical energy here at the furthest point, here halfway, here at the lowest point, and anywhere along the arc is the same number. Okay? If I did 25 joules of work to lift it to here, everywhere along the arc, that pendulum has 25 joules of mechanical energy. Okay? The only thing that changes is how much of it is potential and how much of it is kinetic. When it's out here at its maximum point, it has 25 joules of potential energy. When it's here, at its lowest point, moving the fastest, it has 25 joules of kinetic. Here, I don't know, let's just say it's 12.5 potential and 12.5 kinetic. It probably isn't, but we'll say that's what it is. Okay? Everywhere it goes, that number is going to add up to 25. EI equals EF. Anywhere along the arc, the total mechanical energy is the same number. Because no energy is being lost, no work is being done. I'm not doing anything to this anymore. Okay? Everyone all right with that idea? Okay, so this is what we were just talking about here, okay? If I'm looking at the pendulum here, okay, out here, you know, let's say that this is its highest point, 10 centimeters, okay? Here would be its lowest point. We'd say the height here would be 0 centimeters, okay? It would be swinging along that arc. It would have some combination of potential energy, some combination of kinetic. Maybe it would only have one or the other, depending on where it is. Okay. Mark this one down as conservation of energy problem 2. Okay? This one is as absolutely involved, as complex as a conservation of energy question could get. The good news is, it's only a little more algebra. The concept isn't any harder than the last one. Okay, so I'll get you to copy all that down, okay, including the crappy diagram. So the sledder starts at the top of this hill, okay? We know the hill is 30 meters tall. Do they have potential energy at the initial point? They do. Okay, so we can say that yes, they definitely have EP initial. Right? It also says that they're moving at 1.5 meters per second at the top of the hill. So do they also have initial kinetic energy? Yes, they do. All right. Later, they're moving at 7.5 meters per second, so partway down the hill. The reason I say partway is the question wants us to calculate their height when they're going this fast, which means they have both kinetic and potential energy at that point. Okay, so we can say they have EK final as well as EP final, right? So the givens are VF, okay? This would be HI. This would be VI, the 1.5, okay? We're looking for HF. All right, does it sound like there's any work being done here? No. There's no forces mentioned, okay? No one's like pushing the sled or anything. It just says, here's how fast it was going at the top of the hill. It slides down the hill. It would do that on its own, okay? Somebody just hopped on the sled and down the hill they went. All right, nobody pushed them. There was no work done at all. All right, so in that case then, we can say that the initial mechanical energy and the final mechanical energy are equal because no work was done. There's no mention of energy being lost, okay, or the sled hitting anything and doing work. Okay, it's just sliding down the hill. Now, we just established that at the initial point, the top of the hill, that it has both initial potential as well as initial kinetic. So I can't cross any of those off like I did in the last question. And we've also established that at the end here, at its final point, it does have potential energy because we're being asked to calculate how high above the bottom it is. Okay? They wouldn't ask us to do that if it was at the bottom. Plus, it has final kinetic energy because it's moving at 7.5 meters per second. Okay, so what I'm looking for is this. Okay? How am I going to get HF by itself? let me take a step back here. I'm looking at people and they're looking confused. Okay? And that's probably my fault. Okay, I'm looking for HF. Is that part of this? Right, it would be M times G times HF, which is why I wrote it that way, but I could see that that messed people up a little bit. Okay, so what I'm looking for is part of this term. I want to get that term by itself. How do I get EPF by itself? Right, subtract the kinetic energy over to the other side. All right, so what I'll have is initial potential plus initial kinetic minus the final kinetic. So mechanical energy minus kinetic should leave me with potential energy. Okay? Now I want to blow this up. Not in a bad way. I want to make it bigger. Okay? Do I have formulas for potential and kinetic energy? Okay, that's what I want to put in next. Okay? Just like work energy theorem questions, these are very patterned. There are steps that you go through and you do the same steps every single time. Okay? That's why it doesn't take very long once you've done a few of these to know how to do them all. Right? There's not really a trick to any of them. You just have to follow the pattern. Okay? So for potential energy, M times G times H initial. For kinetic energy, 1/2 times the mass times the initial speed minus 1/2 times the mass times the final speed squared equals mass times gravity times final height. Okay? Now, they told me the mass of the sled. They said it was 70 kilograms, I think, further up. Okay? But do I need that number? In this situation, I don't. I could actually cancel the mass out of every term. Because mathematically speaking, I'm multiplying every one of those terms by the same number, which effectively negates its value. Okay, makes it like it doesn't matter because I'm multiplying every time. Okay? But we'll leave it in for this first one, okay, since we do have the number anyway. I want to get HF by itself. So what do I do with the M and the G? Divide them over to the other side. Okay, now I'm solving for HF. Can't cancel anything now because I got addition and subtraction on the top. So now I have to leave the mass in there. Okay? Can I plug in my numbers now? Yeah, I know all the numbers except for HF. Is this really a lot different than what you did for work energy theorem? It's like a similar pattern, right? It's like set it up at the top, simple, then start expanding it out, expand it out, manipulate and solve. Okay? The trickiest part to these questions is what kind of energy does it have at both points? Just like it was for work energy theorem questions. The trickiest part, what kind of energy is being changed? Okay? So for this one here, we would have 70 kilograms times 9.81 times, what was the height of this hill? 30 meters. Okay, plus 1/2 times 70 kilograms times 1.5 squared. Okay, that's the speed at the top. Okay, move this down. Okay, and then minus 1/2 times 70 kilograms times 7.5 squared. That was our final speed, okay, for the other point on the hill. So just to scroll up so you can see those numbers, okay? 7.5 meters per second was VF. We're looking for HF. The initial height was 30 meters. The initial speed was 1.5. Mass was 70. All right, then I'm going to divide all of that by 70 times 9.81. That's going to leave me with the final height. Okay. Okay, so we got 70 times 9.81 times 30 plus 0.5 times 70 times 1.5 squared minus 0.5 times 70 times 7.5 squared. Okay, divided by 70 times 9.81. Okay, that will need to be in brackets because you want to divide by the whole number, not by 70 and then multiply by 9.81. Okay, so it hasn't gone very far down the hill, has it? It started at a height of 30 meters, and now it's at a height of 27 meters and a little bit, 27.25 meters. So it's gone 2.5 vertical meters down the hill. Okay, so our answer here would be 27.2 meters as our final height. Okay, this is probably the most algebraically involved stuff that you will do in this course. Okay? There's a lot of stuff to move around, but the pattern will always be the same. Okay? All right, questions on what we did there? Okay, I'm going to give you a 5-minute break within the classroom here, okay? And then we're going to move on and just work on some of these, okay? Forgot to record all of that. Okay, so mass 1600, initial speed 5 meters per second, initial height 50, okay? Final height 8 meters, and we're looking for the final speed of the roller coaster. Okay, just going to lay out the first couple of steps here in case anybody's stuck. Okay, is there any work being done in this question? No, there's no mention of force, no distance, no one's pushing it. Okay, it's just going down the slide as it normally would. Okay, since there's no work being done, the energy is going to remain the same. There's nothing there to change the energy of the roller coaster. Okay, so we can say it's EI equals EF. Does it have initial potential energy? Definitely, 50 meters above the ground. So it definitely has initial potential energy. Does it have initial kinetic energy? Yeah, it's moving at 5 meters per second. Okay, does it have final potential energy? Yes, it's 8 meters above the bottom. And since it's lower down on the track and they're asking us for how fast it's going, we should assume that it has final kinetic. Okay? I mean, given the context of the situation, that's the faster spot. That's where we have more kinetic energy. Okay, so we've set that up.
Since none of your givens are 0, can you just assume that you don't have to cast anything?
Yes, because in this case I actually put the numbers on the board, but sometimes I might tell a boring story, right, and say bottom or top, right, and not, or say, you know, it's not moving, it's sitting at the top, and I won't outright give a number, but yeah, you're right in this case for sure. All right, so what I want to look for is VF, okay? That would be part of the final kinetic energy. So how do I get final kinetic energy alone? Subtract the final potential energy over to this side. Okay, that's where I'm going to leave it in case you were stuck. Okay, now you can maybe get going. All right, your next step is to put in the formulas and solve for VF. Okay, so we'll give you a few more minutes on that one. Sorry, my handwriting's not very good here. That's EK final. Okay, so you're looking for VF, so you got to put in your formulas, manipulate, and solve. Okay, so as I said, pattern is basically the same as the last one, except in the last one, we isolated EP final. Now we're isolating EK final. So we're at the point now where we put in our formulas. So that would be M times G times H initial, okay, plus 1/2 MV initial squared minus MG H final equals 1/2 MV final squared. Okay, I want to get V final by itself. What do I do with the half and the M? Divide them over to the other side. Okay, so 1/2 of M comes over here. Now that solves for VF squared. So what do I have to do? Square root the whole thing. All right, so when I'm plugging in all of those numbers, okay, it's going to look like this. Okay, 1,600 kilograms times 9.81 times 50 meters. There's my initial potential energy. Okay, plus 1/2 times 1,600 times, was it 5 squared? Minus 1,600 times 9.81 times 8. That would be my final potential energy. And then I'm going to divide all of that by 1/2 times 1,600. Okay, that's going to, and then I'm going to square root that whole thing. This is probably the trickiest manipulation you have to do in this course. Okay, solving for VF in a conservation of energy question. But it's really not that different than what you did with the work energy theory stuff. All right, so now it's just a matter of punching it all in right. So the way I generally do this is the way you saw me do it here. I punch it in one energy at a time. All right, so I'll clear this and I'll start again. 1,600 times 9.81 times 50 meters. That's my initial potential energy. Okay, it's 784,800 joules. I'm going to add to that the kinetic energy, 0.5 times 1,600 times 5 squared. Okay, so there's my mechanical energy. That's the kinetic and the potential added together. Now I'm going to subtract from that the kinetic energy final. So minus the potential energy final, sorry. So 1,600 times 9.81 times 8. Okay, so that's my final kinetic energy. Now I need to divide that by 1/2 of m. And I got to put brackets there. So 0.5 times 1,600. Okay, that's v squared. So I square root that. Okay, so the speed at the bottom, 29.1 meters per second. Now, so you know, I get that the calculation part can be a bit tricky, punching it into the calculator. It's why a question like this is worth between 6 and 8 marks. Okay? You get a mark for literally every little tedious step in this whole question. All right? That way, if all you mess up at the end is your calculator, well, that only costs you 1 mark for not being good with your calculator as opposed to 8 marks, okay, for not knowing how to start it.
Is it always, like, are we always just trying to look for final velocity or final height, or is that just?
Well, I could set it up so you solve for initial speed or initial height, but yes, you're solving for a height or you're solving for a speed. That's what these are going to ask for. Occasionally, you'd get one that would stop at this step and ask you what's the final kinetic energy. And then you would just have to do all of this without square rooting. Like you just have to go this plus this minus this and you'd have it. I don't typically ask about it. I typically want the speed or height. Okay. All right, so if we were looking at a marks distribution here, you'd obviously get a mark for your givens. Okay, you would get a mark for determining it to be a law of conservation of energy question, and you would get a mark for identifying what types of energy were present. Okay, so that's up to 3. Okay, then you'd get a mark for your manipulation. That's 4. Okay, you'd get a mark for plugging in your numbers. Okay, that would be 5, and then you'd get a mark for your final answer. That would be 6. Okay, occasionally I get like silly generous, and I give a mark for like this step 2, and yeah, sometimes I get a little silly with how many marks you get. It's probably going to be a 6-mark question. All right, so show your work is the moral of the story. Okay, boring story question. Write it down, give it a try. Only way we get good at these guys is to practice. Sorry about your luck. You may. The first little bit of this in case anybody's stuck. All right, so toboggan is racing down a hill. Here's our hill. Here's our toboggan. Okay? At one point, it is 30 meters above the bottom. and moving at 14 meters per second. Shortly thereafter, the sled is moving at 23 meters per second. How far above the bottom is it? Okay, I would say that's probably the final height. Okay, so that would mean that 14 meters per second is the initial speed, 30 meters is the initial height, and 23 meters per second is the final speed. All right, is there any work being done here? No force, no distance, nothing speeding up or slowing it down other than gravity. Okay, so it's a conservation of energy question. Okay, and it would appear like it has both kinds of energy at its initial point. And at its final point, also both kinds. Okay. What am I looking for? Final height, right, looking for final height. So I'm looking for EPF. So I've got to bring EKF over to this side by subtract. Okay, is this pretty patterned? Like, do we do this step basically every time? Yep. I mean, sometimes it's EP, sometimes it's EK that we bring over, but it's the same step. Okay, at this point, can I put in my formulas? Yes. Okay, so M times G times H initial plus 1/2 MV initial squared minus 1/2 MV final squared equals M times G times H final. All right, isolate H final, plug it in, solve. I'll give you 1 more minute. Okay, I'll give you 2.
Where are you?
Okay, ready to go over that one? All right, so if I'm going to isolate HF, all I have to do is divide both sides by M times G to bring it over to this side. I don't have to square root because HF isn't squared. That is the most common mistake I see people do. They automatically square root everything even if they don't have to. You only have to square root if you're looking for something that is squared, in this case, V. Okay, here we don't have to do that because we're looking for H. H isn't squared. All right, so plugging in our numbers here, we will have, oh, okay, sorry, this was the one I meant to talk about because we don't have mass here. Does it matter?
No.
It doesn't, because every single term in this question is multiplied by the same number, mass. So it actually doesn't matter. I can take it out of every single term. Now, you don't have to do that, and on a quiz or a test, I would give you the mass, okay, just so nobody's confused. I accidentally did this on a unit exam one time where I made a question just like this and forgot to put the mass in, and then the first person came up and they're like, Mr. Cooder, I think you forgot to put the mass on that question. I'm like, oh shoot, you're totally right. And I just kind of made up a number off the top of my head, like 80 kilograms. Oh, okay, back to his desk he goes. And then another person came up a few minutes later, Mr. Cooder, I think you forgot to put the mass in this question. And I couldn't remember what mass I told the first kid. And I told him it's like 150, and all of a sudden there were like 5 people in the class whose eyes got like dinner plates. Like, different numbers. I'm so screwed. No, you're not screwed at all. I could give you any number. I could have told you you need 200 million, and you'd still get the same answer. Okay? The mass doesn't affect how fast it's going to go because it's only gravity that's pulling it. Gravity accelerates all things at the same rate, so mass actually doesn't come into play. You will always get the mass, except when I screw up, like this question, okay? But you don't actually technically need it. All right, so we're going to plug in our numbers here. So we'll have 9.81 times 30, okay, plus 1/2 times 14 squared, okay, minus 1/2 times 23 squared, divided by now just g by 9.81. Okay, so 9.81 times 30 plus 0.5 times 14 squared minus 0.5 times 23 squared divided by 9.81. Okay, so final height is 13 meters, 13.0 meters. Now, just to prove to you that mass makes no difference, I'm going to do the same calculation with a mass of 123 kilograms. See if we get the same number. Okay, so we'll go 123 times 9.81 times 30, okay, plus 0.5 times 123 times 14 squared, okay, minus 0.5 times 123 times 23 squared, okay, divided by 123 times 9.81. Oh my goodness gracious, look at that. It's exactly the same number, which confirms mass doesn't really matter. You can put it in if it makes you comfortable. You can take it out if it makes you comfortable. Either way will work. Okay? All right, we will leave it there. I know it's a little bit early, but we'll leave it there for today. We're going to work on that some more tomorrow, okay? And probably do our unit exam review on Friday. So I'll have no quiz, okay? And then Monday, we'll finish up talking about efficiencies, which is like super fast, okay? Super easy concept, and we'll do a little bit more energy and work stuff just to make sure we get it all, okay? Before your unit exam on the 3rd of June. Okay, so that is coming right up.